Okay, now we will continue with some proof of logarithm formulas of evaluating inverse hyperbolic functions, and let me give the first with the which is the sin hx function, okay, and the proof of, let's select the blue pen, but some delay problem about our software, okay, I'm sorry. Proof of first formula, which I talked about at the previous lecture. Okay. Start with the sin hx equals e to the x minus e to the minus x over 2, it equals to y, and the first solve x in terms of y, and I mean that, okay, and the multiplication by the e to the x, okay, and you will obtain the e to the, okay, 2x minus 1 over, okay, 2 times e to the x, and it's equal to y, and the e to the 2x, okay, and the minus 2y e to the x minus 1, it equals to 0, okay, and the set the e to the x equals to u, and after that we can say the u square, okay, and the minus 2y u minus 1, it equals to 0, and the roots of the u's will be equal to minus b, and which is the, okay, 2y, okay, and the minus 2y, and it will be positive, okay, and the 2y minus or plus square root of the discriminant, and which was the 4y square, okay, plus 4, okay, and the 4ac, it was there, and over 2a, and it's 2, so it's equal to y minus or plus, okay, and the square root of y square plus 1, okay, and we know that the square root of y square plus 1 larger than y, and so u1 equals to y plus, okay, square root of y square plus 1, okay, and it's larger than 0, and the u2 equals to y minus square root of y squared plus 1, it's less than 0, and for the first equation and for the first one, maybe we can say the, okay, u1, it equals to e to the x, right, and it's equal to y plus square root of y squared plus 1, right, and take the natural logarithm of both of sides, okay, and we will obtain the ln e to the x, and which is also equal to, okay, x is equal to ln of, okay, and the y plus square root of y square plus 1. Okay, and the second u, okay, for the y minus square root of y square plus 1, okay, and the it will be x equals to, okay, ln of, okay, y minus, okay, square root of y squared plus 1, okay, and this is less than 0, we know that, and so this logarithm, okay, does not exist because of its less than 0. Okay, continue from the first part, okay, and interchange okay, x and y, okay, and so y equals to ln of x plus square root of x squared plus 1, okay, and it's equal to inverse sine hx, okay, and for minus infinity to plus infinity interval, okay, and my friends, omit 3.7 subchapter, which is the second order linear differential equations with constant coefficients. Okay, omit this subtopic. Okay, so you have no responsibility about this subtopic. Okay, and chapter 4, okay, applications of derivatives, and the subchapters, applications of rates of change. Okay, my friends, don't forget, if somebody is speaking about the rate of change, okay, you must understand it's about the derivation, okay? And let me give you some example. Of course, you can find lots of examples in your book, okay? And but I want to give you a liquid of a tank problem, okay? And which is the pumping the liquid. Okay, or the fluid, it can be written, okay, out of a tank. Let me sketch some graph about it, okay, and here is a valve, okay, and this water height, and this is our tank, okay, and the water goes from here, okay, and the height of fluid in the tank, and our tank is cylindrical, and the fluid is pumped out at a constant rate of change, (3,000 liters per minute. And the question, what is the rate of change of the fluid level which is H, okay, inside the tank? That means del H over del T, okay? And let me continue. Okay, solution. We know that tank is a circular cylinder, and the volume of the fluid can be calculated by the 1000 p r square h, okay, and which is the v of h, okay, and the r is constant, okay, which is diameter of the circle, and the del v over del t, it's equal to del over del t, okay, and the 1000 pi r square h, and the it's equal to del over, okay, and the del h, one thousand pi r square h times del h over del t, and the del v over del t, it equals to 1000 pi r square del h over del t, and if r and h are in meters, the volume of the water will be in liters, okay, that's important. And we know that the del v over del t equals to minus 3000 liters over minute, okay, and the minus 3000 equals to 1000 pi r square, okay, del h over del t. So del h over del t equals to minus 3 over pi times r square, an example again. A rising balloon the angle of the rangefinder is increasing at a rate of 0.14 radian over minute when the angle theta equals to pi over 4 radian, okay, and the how fast is the balloon rising at this moment. Okay, and this is the del y over del t, okay, and that's the rangefinder, which is the okay, this, okay, and the balloon is here, okay, and that is the theta, and this point is 500 feet, and y is height, and there's the rangefinder. Okay. Okay, and what can we say about it? And at first we know that del theta over del t equals to 0.14 radian per minute when theta equals to pi over 4 radian. Okay, and we know that y equals to, okay, and 500, we know that because of tan theta equals to y over 500, so y equals to 500 tan theta. This is the trigonometric equality, and the del y over del t, it equals to 500, okay, del over del t tan theta, so it's equal to 500, okay, times del over del theta tan theta, del theta over del t, okay, and it's equal to 500 secant square theta del theta over del t. It equals to 500, okay, and we know that the theta is pi over 4, okay, secant square pi over 4, okay, and del theta over del t is 0.14, okay, so it's equal to 500 times square root of 2 square point 0.14, okay, 0.14, and it equals to 140 feet over minute. And then now let's continue with the extreme values. Okay, you can find lots of examples about the rates of change. Okay, and please look at the exercise 4.1. Okay, it's important. You will find the 41 different problem. Okay, and this will be good for you to understand rates of change chapter. Okay, and I want to continue now 4.2. Extreme values, and I mean that from the extreme, maxima and the minima. Okay, and the definition: a function f has a local maximum value at an interior point x equals c of its domain if f of x less than or equal to f of c for all x in some open interval about x equals c I mean that the okay, and this point is A, this point is B, okay, and the C, okay, and the for this interval, C is the local maxima point. And this point is local maximum point, okay, and maybe as you see this is the y max, and we will call this C point is the okay absolute maximum point after that. And the local, let me continue about this, but this point is not an absolute maximum, okay, and the local maximum value is called the absolute maximum okay if the interval about x equals c covers all the domain of f function. Okay, and so we can say this is the absolute maximum, okay, and the similar definition is given for minimums, okay, with a change okay f of x larger than or equal to f of c, okay, only that. And the samely sketch it, okay, and for example Okay, this is A, this is B, this is C. Okay, and for this interval we can say C is a local minima point. Okay, also we can say for A point, yes, it's local minima. Okay, but only we can say for the C point, yes, it's absolute minimum point. Okay, okay, and let me give you another definition about the critical point. The points in the domain of F where del F over del X equals 0 are called the critical points of F, and we denote that by the CP, okay, critical point. And another definition, sorry, the points where del F over del X fails to exist are called the singular points of F, and we will call that by the SP points. Okay, and the only places where a function F can have extreme values one, interior points where del F over del X equals to 0, if and only if critical points. Okay, and the second, interior points where del F over del X fails to exist if and only if singular points. And the 3 endpoints of the functions domain if the interval is closed, okay, it's equal to if and only if endpoints, and also it can be called by the critical points of the function. Okay, and let me sketch a graph, function graph, and to understand the critical points and some local and maxima, local minimum and local maxima points of the graph. Okay, and for example, we have lots of points like that. As you see, this point is A, x1, x2, x3, x4, x5, x6, x7, and the B point. Okay, and we can say for the x1, x3, x5, okay, x1, x3, x5, and x7. Okay, are local minimum points. Okay, and the x2, x4, x6, A and B, okay, are local maximum points. Okay, and we can say for the x6 is absolute maximum point, and for x5 is absolute minimum point. Okay.